Yes, applying machine learning to structured time-course sensor data for improved chemical outcomes and reproducibility. If only I could have thought of a larger title, I would have shoved that in as well. I'm usually one for fairly snappy titles, but there we go. I guess a lot of words conveys a message. As you say, I'm the data science manager at DeepMatter. And I guess the first thing I'll do is give a quick, brief one-slide overview of who DeepMatter are. DeepMatter are a company that formed in earnest, let's say, about 5 years ago. And we spun out of the Cronin Group at Glasgow University, and our key focus is on the digitisation of chemistry and tackling reproducibility problems and all the various aspects of those problems that revolve around the lack of knowledge transfer that's present in chemistry and that wider area. So yeah, we focus on improving productivity throughout the discovery through to the process phases of chemistry with various tools, different tool sets along the way, helping our customers. We have a hardware platform, we have a software platform which is cloud-based, that's DigitalGlassware. What it does is it allows chemists to encode their chemistry as recipes, as we call them, and it allows us to capture data from our own bespoke hardware, but more to the point from off-the-shelf hardware, which is integrated into the platform. So, you know, things like, obviously temperature, the most interesting of all the things, but, you know, we've got things like color information, UV light levels, integration with pH devices, as we'll see a bit later on. But that extends out into even other fields, like, you know, maybe talking to an NMR machine and things like that. The purpose of all this is, yes, it will help your chemist have insights into their chemistry that's being performed and push forward the project. So, you know, quicker returns, you know, because really one of the things which we focus on is how can we reduce wastage, I suppose, where wastage is obviously chemically, but really time wasted. That's one of the things which we focus quite acutely on as part of the platform. What you get at the end of that is a database, right? And that database contains all the recipes, which I was talking about. It contains all the sensor data that I was talking about, and it will contain other things that you've added along the way, like what percentage yield did I get out of that reaction? What did I get out of the variation of those reactions that I performed as well? And you can use that for computational chemists to find that data set and have some insights. The other side of the business is Infochem, and we've got a flagship product which I won't spend much time talking about, IC Synth. It's our retrosynthesis tool, and it's well, we believe it's industry leading, right? I guess everyone says that, but we believe it, and we're quite firm on that. I'm not going to talk too much about it, but it's interesting to hear discussions on building blocks, because that's exactly what IC Synth does. But without much further ado, I will skip on to the bulk of the talk. So what I'm going to talk about mainly is a case study, or some case studies, but really one primary case study, which we performed about a year ago, and it's focusing on the root of the company. It's the digitization and reproducibility issues, and we basically needed to prove to ourselves, right, that what we say we can do, we can do. So what we did was we set out to develop a chemistry procedure and a piece of chemistry work which would show this in action. We worked with O2H over in India to partner up with them to perform well, we'll get onto it in a second, but a particularly capricious piece of chemistry, which is known to be problematic. And obviously, we're going to go through the whole process of encoding and digitizing the recipe, capturing that sensor data, and then at the end, we're going to do some machine learning on it, because we wanted to know well, we've done this. Can we get something extra out of it? What can we do with our modeling capabilities? So in particular, and I'm going to first off say I'm not a chemist, so please don't ask me chemistry questions unless they're revolving around data science. The particular piece of chemistry we performed was a Bookville-Hartwig coupling. You can read about it there, and I'm quite sure you know more about it than I do. But the point is that this was chosen because it's very temperamental, and you can seemingly repeat that chemistry multiple times and get results every time. So it's a pretty good candidate for showing off that, you know, if you actually do digitize things, if you have a solid reference for your previous runs, which you refer to, then you can say at a later date, I can see the differences between these runs. So in the next run, I'm going to focus on maintaining temperature, or I'm going to focus on addition rates and drop-wise rates, that sort of thing. And through that, you can correlate that back to your ultimate yield and your ultimate purities that you get. So to prove our point that digitization is good, which I've yet to find an audience that isn't receptive to that line, but to prove our point, we first said, okay, well, let's do it as it's on the paper. Let's do it as it is actually published. And we'll do it no digital capability at all. It will be the chemist in the lab, piece of paper, run the chemistry, right? And we did that in triplicate. And every 30 minutes, I think it was, we sampled with HPLC. So that way we could get a picture of what was happening over the duration of the project, of the run. Once that was done, we got chemist B to come in, and they digitized the paper, the protocol. So they entered it into DigitalGlassware and removed the ambiguity, I suppose, almost, and made it into a searchable record, which could then be branched, which could then have modifications done to it, different versions. And they executed it multiple times as well. And they did it to the point where they were happy that it was as they would like it to be, by which I mean just because it's in a paper and it's written that way, don't necessarily mean that's how it actually needs to be executed in real life. And we found there was a couple of little adjustments that need to be made. Then, once done that, we got some outcomes from chemist B. Chemist A was told, okay, can you now run the recipe with the digitized version, and we'll compare the results that come out of the digitized versus non-digitized versions, and how did that transfer of knowledge, how did that go between chemists B through to A? And again, we'll talk about some machine learning stuff. A little bit on the chemistry. As I said, we call them recipes. Seems to have become the standard nomenclature actually over the past few years, so I'm probably going to stop italicizing it. Essentially, it's a piece of XML that sits in the background. That kind of removes all the fun from it when you say stuff like that, but actually, if you say to someone who's a computer scientist, like me, or once was a computer scientist, oh yeah, you can like search that record and it's totally structured and it's easy to index. You know, they'll bite your hand off to get hold of that stuff. And that's how we're going about the digitization process at DeepMatter, at InfoChem. What we want to do is create something which is easy to disseminate and therefore recreate at different sites, at different companies, in different universities. And all of that is stored on our cloud platform, so it's secure and it's easily shareable, and that's really what sits underneath all of what I'm going to talk about today. Now, I'm not going to sit and bore you with looking at XML schemas, because you know I get excited about the possibility of an XML schema, but I don't want to go and read it. The real message here is we're moving away from that sketch and text style of notepads, and we want to move into the digital era, right? You know, it's 2021. There's an example of exactly what we got. I expect that's familiar to an awful lot of you. And that transforms into the digitized version on the right in DigitalGlassware. And you could conceivably have a one-to-one mapping of what's in that written notebook into the digital notebook, but I suspect that there are more things that will appear in your digital notebook over time than would have appeared in your corresponding paper notebook. And the beauty of that is that you can track all the changes you've made. You can track all the versions of recipes you've done. And altogether, you just get a better experience at the end. So essentially, we did multiple runs, as I've alluded to, and we sampled real-time sensors from our own device X device, which is what you see in the top right here. It's a combined thermometer, UV measurements, cameras, stir rates. It's a sort of all-in-one device which we used. But we also had other devices in there. We had a pH sensor, which was an off-the-shelf device. And as I mentioned as well, we're also sampling with the HPLC every 30 minutes. We get a lot of data out of that, right? I think, how many did we get? I think we did in the tens of runs. I can't quite remember. I think it's mentioned in later slides. But it's a lot of data. It's particularly a lot of runtime data, a lot of sensor data that's coming in. But we'll have a look at that in a second. The outcomes, well, the headline result goes up first, right? And thankfully, it's what we all want to hear. It's that digitization is better than not digitization, because in general, what we saw was that the average yield was improved and that it was more consistent as well. The error bars on that Chemist A run, the blue ones, are horrifying to me. But I'm, again, not a chemist. I don't know, maybe chemists in the room are like, yeah, I get that. But to me, that's horrifying to have like a 15% standard deviation across things. Whereas it's much, much tighter. These are aggregated over all of the runs, which were, as you can see, circa 5 hours. So that's the headline measurement. That's wonderful. The company can continue this. But let's go and look at some more interesting things that actually came about from it. So the structured data set, I've been talking about the recipes. As I say, buckfold couplings. Once we've got the recipe digitized, actually lots of things become possible. We don't even need to do any chemistry yet, really. It'd be nice if we did, you know, nice. But we don't need to strictly, because you've now got a searchable data set that you can use. You can actually use that if you trust your chemistry, if you trust that recipe. You can actually start using it in text mining. You can use it in fingerprinting of the molecules, do some searching for similar reactions, all that sort of stuff. That's actually quite an exciting possibility, because we have massive chemistry databases kicking about with no runtime data. They may have a couple of outcomes. They may have some hints in them about how long the chemistry took, or, you know, this was done at 25 degrees. But they're usually all in a fairly unstructured textual formats. And once you've got that coded into that nice XML standard, it really, the world opens up to you. But anyway, I'm waffling about that. As I said, we've got multiple sensors on the go. The recipes, so this is the key part of recipes. They give context to your sensor. If you've ever looked at a temperature profile over 24 hours, for the sake of argument, and you know that it's not just sitting there stirring, you know that things are happening, things are going in, perhaps samples are being taken, the lights have gone off in the office, stuff like that. The recipe gives you context on what's happening there. It tells you at 1659, we added this many milligrams to the beaker. At 1745, we mixed it for 60 minutes. That sort of information, and that's really crucial when it comes to doing the analysis. So I'll give you a very brief overview of what we did with some machine learning modeling on this, and I'll just mention that we are going to do a white paper at some point on this. So What is that image, as I'm sure some of you are saying? Well, the first thing in any data science problem, as far as I'm concerned, is visualize the data. Some people can think in high dimensions, some people just know it's in their data. I'm a simple man, I need to see a picture. So in this case, what we did was sensor data. So it's our temperatures, it's our immersed temperatures, it's exposed, it's our ambient humidity, it's the pH levels, it's the color levels, all the things which you've sampled. And we map those across the operations which we saw executed in the recipe. And the timestamps accordingly. And we extract features from it, like what was the median temperature during this particular phase of the chemistry, what was the light level, what was the red light level in the beaker over this particular phase. And we visualize that using some machine learning algorithms. This particular one is TSNE, for those who are interested. And there's circa 100 data points in there, I believe. And really the reason we do this is so we can prove to ourselves it's worth going ahead, right? There's no point in proceeding if there's absolutely nothing in there. And there's enough in this information that we were happy to go ahead. So if you were to look at the top right diagram, let's say for the product formation, you can see that there's this bleed from, on my screen anyway, right to left, as product is formed. And if you were to look at the bottom right, which is a particularly difficult one to interpret, I'll give you, that's the color of the variant of the recipe. So it's interesting that all the variants which were of the, let's call it blue variant, were all actually quite similar to one another in that they form a pattern. And the other ones, the other variants of it, are all put off to the side. That's an interesting pattern. So I'm going to skim over this one fairly quickly because it's a bit dry. But I'm sure you probably all know, if you've ever done any data analysis, the cool bit comes at the end. All the wrangling starts, all the wrangling of the data comes first. There was quite a lot of wrangling in this. So when we were looking over this data, the key thing which we identified was, it looks like the hold phase of the chemistry has a temperature hold phase of 3, 4, 5 hours, depends on how long you want to run it. But that's when the product is formed. That's the important bit. So that was the bit which we focused on in terms of doing the actual modeling. We correlate that to the HPLC data, which in this case I think is the yellow bars, if you can make those out. But the point is, it's every 30 minutes. And again, we're going to use the same data set which we used in that visualization, which I showed you a moment ago, and maybe append in a few more features as we go along. But that's going to form the basis of what we want to actually do our modeling on. But what is the modeling we want to actually achieve? Well, the most interesting thing, I think, for most chemists is, can you predict the yield? So this is an interesting problem for this particular piece of chemistry because it's so capricious, because you don't know if you just are sitting there watching it spin with no digitization, no sensors, what is actually happening in that thing. I'd have to sample it with my HPLC to find out, but HPLCs are hard to come by, and yeah, it's getting used by the other team and it won't be free for quite a while. Wouldn't it be great if we could just had a system which could just tell me how much product was being formed based on historical runs? And that's essentially what we've managed to produce here, based purely on the runtime data. So the temperatures, the colors, the UVs. We took all that data again, and we run it through, in this particular case, it was a gradient boosted regression tree. It wasn't XGBoost, for those of you familiar with that, but 6.5 dozen, right? And what we got out was a fairly good approximation of the true yield over time. Yes, there's a bit of noise in there, so that the orange line is a predicted one here, but it does seem to map across really well to the actual yield that's being generated at runtime. We've got below 3% mean absolute error, which is pretty good, given that if you remember those error bars back at the start, they were like plus minus 10, 15% of median. There's no killer feature in here though, which was surprised because perhaps with my bias, I went into saying, well, obviously temperature is the most important thing here. Obviously it is. But it turns out that it's not like it's the thing which is, you can't get away with just modeling temperature versus yield, put it that way. You need to have that additional information of what is the UV, what is the color change that's occurring over time. From what I remember, what tells you there, temperature was highly ranked, but UV was actually also a good indicator of progression. My suspicion on that one is that it's because of the color change that occurs during the reaction, and that's a bit of a proxy for it. So we have got a camera on device X, which we use for detecting color. However, the color was quite inconsistent actually throughout the multiple runs that we did, the 11 or so runs. But the UV was much more reliable. So the camera is somewhat affected by, is someone pointing this at a window? Is it in shadow? That sort of thing. Whereas the UV itself has much more, much better trends inside it, which are comparable across runs. But the real bottom line here is that we managed to produce something which we could actually integrate into this particular piece of chemistry, so that at a later date, someone can run this and say, I don't have access to my HPLC. I'd really love to be able to have an idea of how far along or how much yield I've actually produced at this point. And that leads on to the next question of, well, it's good that you can tell me my yield, but can you tell me if my chemistry is failing? That's almost the same question as far as I'm concerned, certainly in this context. So when I say failed, what I really mean is, has it stopped doing what it's doing, right? Failure, I suppose, is a loaded term, right? That's up to you whether or not you think 40% yields a failure, or 10% is a failure, or 90% is a failure. But it would be good if you could tell me when it stopped producing any more product. And we found out that it actually probably could do that. And it could do it in some cases almost more reliably than it could tell you the yield. So again, same data set, we fed into it, and we fed into it in this context. It was the label was indeed the conversion, which had occurred over time as sampled from the HPLC. And really what we want here is the trend. So you may notice in that graph on the right that there's a fairly large mean square error. That's because mean square error is horrible. Mean absolute error is much nicer. But what we're getting is that at the end of it, the prediction tails off, right? So it's recognized that actually the chemistry is completed. And I should also say that there's no explicit concept of time in these models. So it's not like it's just saying, well, yeah, 5 hours have passed, of course it's finished. It is actually, that has been removed. Certainly it might be kicking about implicitly in some of the other ones, but it's certainly not explicitly represented. And yes, it shows a slightly better result in some cases than the yield modeling. But wouldn't it be great if your model could just say, I think your chemistry's finished. I don't necessarily know how much you've got in terms of a percentage yield, but you're done, right? You can clock off, you can go home, or you can get another run in, because wouldn't it be great, instead of having to mix for 40 hours, wouldn't it be great to just be told 2 hours in, it's finished, just do another one. So the third piece of analysis we looked at was far more scoped towards process style chemistry. So the whole sort of project itself is kind of focused on process style chemistry, but this one's very much focused on it. So what we wanted to do was say, well, I've got this run, and I've got these temperature traces, and I've got these UV traces, and I've got these color traces. If I can pick out the ones which I know are good, wouldn't it be nice if the system told me if I'm deviating at a later date from expected behavior? And it turns out that's actually more than tractable when it comes to, once you get access to that sensor data, you can actually develop really good models of normality, if you like, in your reaction. And the way we did that was, well, I won't bore you with it, but essentially we're using the recipe. Remember, I was telling you about contextualized timestamps. Well, if you can use those timestamps to actually squeeze and tug and pull at your sensor data, it becomes much more manageable and comparable across runs. So what we get in the top right here is the temperature trace across all of the runs, and you can transform that into an almost swimlane style representation on the bottom there, and that allows the system to flag you when you're going outside of your expected behavior, because that could be a correlate for a lower yield or possibly safety considerations. You know, if a couple of degrees sometimes can be the difference between something working and something exploding. But that's something which we very much are thinking about integrating directly into the platform. So that was the first case study. And I've got a couple of minutes, so I'm going to wang in a couple of extra things because I'm always keen to show off a cool graph, right? So this is very brief, these two. The case study here is we were working with a large pharma partner who I will not name, and I will not give any details on the chemistry either, but we were working with them using the pH sensors, and in this particular context, we were looking at color change. And the feeling was we've got this novel piece of chemistry which we are trying to execute, but we know nothing about it, right? We don't know anything about it. We know that the literature says stir for 20 hours, right? Wouldn't it be good if we could actually get some information out of it? Because there was a feeling that something could be done with it. So we repeated the chemistry with DigitalGlassware, with the device X in place, with a pH sensor in place, and we discovered that actually the reaction's done after 20 minutes, and that's quite a difference in time scales, right? Talk about getting one extra run in before your shift is done. Well, now you can actually achieve dozens of runs in one day, and we found some interesting correlates for the yield forming over time. So the temperature, obviously, there's an exotherm that occurs, and once that tails off, then essentially you're done. There's a color change that occurs, which you can see in this particular image. It's sort of basically darkening down from a deep orange color. I believe it starts off yellow, it becomes a really deep orange color, as you can see from the red, green, blue signals. But there was also a change in the pH, which nobody knew about. That was completely unknown. And if you were to ask me which one's the most reliable, I would just immediately say, well, the pH is definitely the one which you want. But that's the kind of information you only get once you execute your chemistry with real-time sensors. But that's enough on that. I really like this picture. I just want to talk about it. Case study 3 is reaction space visualization. So we've got access to digitized recipes. At DeepMatter, we've also got access to Sprezi, which is the world's 3rd largest reaction database. And we've got access to it because it's ours, right? So what we wanted to do was say, well, let's take Sprezi and let's take the data in DigitalGlassware and let's try and visualize it, because I sometimes hear people talking about visualizing chemistry space, and I've never really seen a good picture of chemistry space because it always looks too small and narrow. So this image you see on the top right is about 99.9999% of Sprezi, which is circa 4.5 million reactions. I won't go into too much detail on what the features are in this case, but it's using the same algorithm. Actually, it's not true. It's not using the same algorithm as we looked at earlier for the visualizations. This is using UMAP, which is essentially the successor to TSNE. And what we wanted to do with it was say, well, can we find out interesting patterns in our own data? And again, I'm not going to go into too much detail on what we're actually looking at, but we were able to do it. We were able to achieve it. So that image in the top right there, you can see that there's clusters in it. You can see there's a central core of blue points. I won't bother explaining why they're blue. But that structure which exists in there is that we were able to go and actually start picking through our own databases visually at the macro level, and start making interesting observations about, oh, this reaction here perhaps could be identified better if it had additional features in it. This reaction shouldn't be here at all. All the ones in this cluster are just wrong in some way. Or we can say, oh, why are these points over here? Why are they next to these points here? Oh, it's because they've got this particular type of behavior. And that sort of information allows us to start saying, okay, well, can we visualize movement through this experimental space? Is it possible that we can actually start moving from just visualizing the data and the movement through it to actually a more generative style model, which would come from something else? But it would allow us to say, well, if we've got this portion of the space and this portion of the space, wouldn't it be nice if we could actually explore the portion in the middle? But the point is, all of this is only possible if you start digitizing your data. It's having done it, it's essentially impossible to do it from paper records. So the digitization is definitely what I'm always hammering home to people, because this is the kind of thing that becomes possible once you can do it. So a very brief summary. I believe we're about to wrap up. In general, across the whole talk, we've been talking about the project Crocus work, which we did at O2H. But all that came about from chemistry being an observation-based science, which can often lead to poor reproducibility, right? By capturing your data in the likes of DigitalGlassware, you can disseminate that information much more easily to your colleagues and to other teams and universities and publications. Why not have a digital record go up when you publish your paper and say, look, here it is, I have the proof of what I did. You can't accuse me of being wrong. Once we've got that in those standards like XML, which we've got PCML and PCRR, which are just fancy names for our XML standards, we can share that with third parties as well. So we can integrate it into your external ELNs, let's say, in other systems. And the point being that the time course data allows you to actually in real time visualize, and through all of that, that's when you can start doing the machine learning. That's when you can start doing AI. That's when you can start actually getting insight into your data. Because, and it's big bold in letters here, but Industry 4.0, not a fan of buzzwords, but it's coming, right? Or it's here, I suppose. These are the types of tools and datasets which will basically form the foundation of that industry. And it's the kind of thing which we're obviously really keen on pushing ahead on, but it's something which I would encourage everyone to be aware of going forward, because it's either jump on the bandwagon or get left behind, I think, at this point. But that's everything I'm going to cover today. If you get any questions, I'll be happy to try and answer them.